Section 5.3 is called the real zeros of polynomial functions. With this assignment, we are going to focus on synthetic division to divide polynomials, and then we're going to look at the remainder theorem. And then using synthetic division, we're going to locate the zeros. We will talk about potential rational zeros, how to find them. And then towards the end of the assignment, we're going to actually find the real zeros by using synthetic division and the potential zeros theorem. So we have total of 10 questions on this assignment, and then our first focus is synthetic division. So the first question here says that use synthetic division to find the quotient and remainder when this function is divided by x minus 2. So whenever you want to perform a synthetic division, first you have to make sure that your function is in standard form. When I say standard form, it needs to be ordered from greatest power to the smallest power. So in this case, it looks like it is okay, x to the 6th, x to the 4th, x squared, and we have the constant at the end, but it is missing some terms. For synthetic division, it is important that for whatever is missing, we put a 0 as the coefficient for that missing term, and we write the function in fully form. Again, so for question 1, I am going to actually switch to this bigger document. So maybe we should just actually bring the question to the other paper to have enough space. For this one, it's just asking the quotient and remainder. And then when I bring this question to this bigger paper to have more room, okay, so when we want to solve this question first, let's put the function in the standard form. So the highest term is, the highest power is 6x to the 6th. We call this as leading term. Now, I don't see any x to the 5th. That means we have 0 times x to the 5th. We have 0x to the 5th. Then we have 4x to the 4th. 4x to the 4th. So this needs to be a 4, not a 9. So we have negative 4x to the 4th. And then we have 0x cubed, because we don't see any x cubed in the problem. And then we have 8x squared. We have 0x. And last number I see is 8. So it's important that first I write my function in standard form. Now for synthetic division, I don't need everything. I just need the coefficients in front of each term. So I have 6x to the 6th, 0x to the 5th, negative 4x to the 4th, 0x cubed, positive 8x squared, 0x, and the last number is 8. These are the numbers that we're going to divide, and we're going to divide them by x minus 2. So when I set x minus 2 to the 0, that means x must be set to a 2. So the number I need here is 2. Again, this number will be derived by setting x minus 2 to a 0. So that's what I need to place here. Now for the synthetic division, the rule is first, the first number always moves to the bottom. Without doing anything, 6 will be just copied to the bottom. Then we will do 6 times 2. So 6 times 2 is a 12. Then I need to add these 2 up, which gives me a 12. Again, 12 times 2 is 24. Add them up, positive 20. 20 times 2 is 40. Add them up, a 40. 40 times 2 is 80. Add them up, 88. 88 times 2 is, I believe, 176. Add them up, 176. One last time, 176 times 2 is, this is getting really big, but it's okay, 352. Now when I add 8 and 352, that's a 360. For synthetic division, last number at the end is always your remainder. Whatever you get at the end is always your remainder. And then quotient, which is the answer after you perform your division, the quotient will be generated by using these numbers. Synthetic division says that whenever you divide an x to the sixth by x, your answer has to always start 1 degree lower. So because the question is x to the sixth power, I am going to have 6x to the fifth plus 12x to the fourth plus 20x cubed plus 40x squared plus 88x plus 176. This whole thing is gonna go under the quotient. And then for the remainder, we have just one number for the remainder, which is 306. And this is how we're gonna handle question 1 on the homework. So you have a box for quotient and you have a box for remainder. Now the question 2 says, use the remainder theorem to find the remainder of when f of x is divided by x minus 2. So f of x is given here. We're going to use the remainder theorem to find the remainder when f of x is divided by x minus 2. Then use the factor theorem to determine whether x minus 2 is a factor or not. So we have two theorems here we need to learn. Remainder theorem is when you divide this function by x minus 2 using synthetic division, now you know how to find the remainder. But the remainder theorem says that if you don't want to do the synthetic division, if you just plug in a 2 to the function, you're going to straight find your remainder. So that's what the remainder theorem says. Remainder theorem says, don't do the synthetic division. Instead of x, just plug in 2. Where did the 2 come from? If you set x minus 2 to a 0, x equals 2. If you plug in 2 to the function, you will find your remainder. That's the remainder theorem. And the factor theorem is, if your remainder is a 0, x minus 2 is a factor. If your remainder is a number different than a 0, x minus 2 is not a factor. So that's how we're going to handle question 2. Again, for question 2, I believe like I am going to need a bigger space. So I'm just going to copy this on a bigger paper first. So I'm going to copy the question over here. Okay. So first question here is, what is the remainder when you divide f of x is equal to 4x cubed minus 9x squared minus 4x plus 15 by x minus 2? This is the first question. To answer this question, we can do two things. We can first do synthetic division, if we like, by synthetic division. I can answer this by synthetic division. I can find the remainder by synthetic division, or I can find the answer by remainder theorem. So the remainder theorem says you don't have to do the division. Your remainder will be the same number as f of 2. Again, where did the 2 come from? If you set x minus 2 to a 0, x equals to 2. So if you just evaluate your function when x is 2, which is 4 times 2 to the third power minus 9 times 2 to the second power minus 4 times 2 plus 15, and then simplify your answer. This is a 8, 4 times 8 is 32. This is a 4, 4 times 9 is 36. This is an 8, and this is a 15. If we just organize these numbers, that's a negative 4, negative 12. So f of 2 is equal to a 3. That makes your remainder to be a 3 as well. So the remainder must be 3. Let's prove that this answer will be still 3 when we do the synthetic division. So how we do the synthetic division? First, the function is in order from greatest power to the smallest power. And we have all the terms we need. We have the x cubed, we have the x squared, we have the x, and we have the constant. So I don't need to plug in a 0 for any term. So we have 4x cubed, negative 9x squared, negative 4x, and the last number is 15. And then we want to divide this function by x minus 2, so that makes your x value to be a positive 2. Bring down the first number, multiply, add, multiply, add, multiply, add, and what you notice is we got the exact same thing. And then for synthetic division, the last number always represents the remainder. Remainder is equal to 3 by actually performing the division. But according to the remainder theorem, you don't have to do this division. If you just plug in 2 for x and evaluate your function, you will find your remainder immediately. Now, the second question is, then what do you think? Second question is x minus 2 a factor of f of x is equal to 4x cubed minus 9x squared minus 4x plus 15? And our answer to this question is a no. So our answer will be a no. No, because if x minus 2 is a factor, the remainder must be a 0 by factor theorem. If it is any number different than a 0, if your remainder is any number different than a 0, it will not be a factor. But if you get a remainder of 0, you will call, yes, x minus 2 is a factor. But in this case, we're just going to put no for this question. We're going to say no because remainder was 3. It wasn't a 0. Very similar question for number 3. So I think to have enough space, we want to bring question 3 over here. It's another function that we have to work with. And then this time we're going to check it for x minus 3. So we're going to use the remainder theorem and we're going to use factor theorem. So let's just bring this question to a bigger space. For question 3, first, I want to decide what is the remainder when I divide this question by x minus 3? Again, you can use remainder theorem or you can use synthetic division, but because the homework specified remainder theorem, I will just find the remainder by using the remainder theorem. So according to the remainder theorem, the remainder can be calculated using by plugging 3 into the function. So f of 3, if I calculate f of 3, I can find the remainder. So I need 2 times 3 to the 4th power minus 5 times 3 to the 3rd power minus 14 times 3 plus 15. And I just have to evaluate this expression. That's 81. 2 times 81 is 162. That's a 27. And 5 times 27 will be 135. And then 14 times 3 will be a 42, and that's a plus 15. This is a lot of numbers to add and subtract, but we'll do it. 12 minus 5 is 7. 5 minus 3 is 2, so this will give me a 27. And then I have a minus 42 and plus 15. I think I want to just go ahead and add these two positive numbers first, which is going to give me a 42. And then when I minus 42 from them, I get a remainder of 0. So this means this time the remainder is 0. And the question is then, is x minus 3 a factor of this? I'm going to say yes, because this time the remainder is 0. So we're going to say that x minus 3 is a factor. For question 4, it's the same type of question, and then we have just a different function, and we want to decide now if x plus 1 is a factor. So to find the remainder, let's again find f of negative 1, because when I plug in, when I set this to a 0, x will be equal to a negative 1 this time. So we're just going to go ahead and plug in negative 1 for x. So I need 4 times negative 1 to the 6th power plus 11 times negative 1 to the 3rd power plus 7. Negative 1 to the 6th power is still positive 1. 4 times 1 is 4. This is a negative 1. When I multiply it by 11, it gives me a negative 11, and this is plus 7. So that's a -7. -7 plus 7 is a 0. So indeed, this time the remainder is still a 0. So that makes x plus 1 a factor of this polynomial. Question 5 is understanding this idea one more time. So I am going to scroll down to question 5. It's the exact same type of question. We're going to find the remainder using the remainder theorem, and we're going to decide if it's a factor or not. So x plus 3 is what I want to check. So if I take the x plus 3, set it to 0, the x value I need to use in this problem is -3. So for remainder, I need to find f of -3 first. So f of -3 will be calculated using 3 times -3 to the 6th power minus 27 times -3 to the 4th power plus -3 to the 3rd power minus 1. These are very big numbers, but we can do this. This is 3 times, and then this is 81 times 9. That's a 729. This is 81. And then this is 27 times 81. This is a positive number. We are multiplying by a negative number, so that will be a negative. And I will need here 27 times 81, which I want to just write it as 3 times 729 again, because this is 3 times 9. And I just multiplied 9 by 81 here. And I realized that these two are actually the same number. Here, these two is -27 and -1. So this one and this one will cancel out, and the remainder to be a -28 in my case. Because remainder is not equal to 0, we're going to say x plus 3 is not a factor, because if it was a factor, the remainder had to be a 0 for this question. That's how we do number 5. When we scroll down to question 6, this now talks about a different objective for this section 5.3. How do we find the potential rational zeros for any polynomial function? So we're not going to find the actual zeros, and we're going to find the possible rational zeros. To decide the list of possible rational zeros, we will always look at the first number, the last number, the constant. The constant in this case is 1. And then we're going to find the factors of 1. I can divide 1 by 1 only. This is the only number I can divide the 1. 1, the factors of 1 is +1 or -1. Then we have to find the leading coefficient, which is the number in front of the greatest term. So 7 is the leading coefficient, and the factors of 7 is 1 and 7. So I can divide the 7 by 1, and I can divide the 7 by 7. And we just have to think about both the positive version and negative version. Now, to find the possible rational zeros list, we will stick with 1 and then divide it by this first number. 1 divided by 1 is 1, but we're just going to think both the positive version and negative version. The other thing is 1 divided by 7, so plus and minus 1 over 7. This is how I can find all the possible rational zeros here. So for this question, I will just pick C. -1 can be a rational zero for this problem. What does rational zero means? -1, when we divide this polynomial function by -1, the remainder might be a 0. Or when I divide this function by a +1, the remainder might be a 0. Or when we divide this function by -1 over 7, then the remainder might be a 0. When I divide this function by a +1 over 7, then the remainder might be a 0. But with no other number, when you divide it, will give you a remainder of 0, which means these are the only solution zeros, that they are the candidate for this function. For number 7, it's the same type, but different numbers. We're going to practice this one more time. So I always look at the last number, 3. And then the factors of 3 is I can divide the 3 by 1, or I can divide the 3 by 3. So these are the factors of 3. Then I need to look at the leading coefficient. So we have 1 times x to the power of 9. So the leading coefficient is just 1. And I can divide 1 by only 1. So I'm ready to create the list now. List will be created by dividing 1 by 1, which is just 1, and then dividing 3 by 1, which is just 3. So we will have positive 1, negative 1, positive 3, negative 3. This will be the possible rational zeros for this function. Okay, number 8 is the same type, but different setup. Again, the last number is 2. I'm going to divide 2 by 1. So the factors of 2 is just 1 and 2. These are the only factors of 2. And the leading coefficient here is negative 4. I can just take it as a positive number since I'm considering about the negative and positive form of this number anyway. Factors of 4 is 1 and 2 and 4. These are all the factors of 4. Now, when we want to create the list, we always start the top number to bottom number. So 1 over 1 is just 1. Next, I need 1 over 2. So 1 over 2 is the 1 out of 2. This is a fraction. Again, I'm going to divide 1 by 4 this time. So when I divide 1 by 4, I get 1/4. Okay, these are the only possibilities I got from 1. There's another number waiting for us. The next number is 2. We're going to divide 2 by all these 3 numbers this time. 2 divided by 1 is 2. 2 divided by 2 is 1, but 1 is already in the list, so we're not going to repeat it. And then 2 divided by 4 is the same fraction as 1/2, but it's already in the list, so we're not going to repeat it. That means the possible zeros are positive 1, negative 1, positive 2, negative 2, negative 1/2, positive 1/2, negative 1/4, and positive 1/4, which makes my answer to be a C. For question 9, this time we are going to actually find the zeros of this function. So it's not in factored form, so I can't just take each factor, set it to 0, and find the solutions. This question wants me to find the real zeros for this function. And then once I list the real zeros, I'm going to give them the factored form. Since this is going to take a lot of space, I would like to just copy this question on a bigger piece of paper. So we're going to find the zeros of this. Okay. So to find the zeros here, first thing is I am going to find the candidates. What numbers can be there? So first step, list the possible rational zeros. So we will focus on first possible zeros, possible rational zeros. So first we're gonna decide what numbers can be our solution. In order to do that, I'm gonna look at the last number 77, and I will find the factors of 77. I can divide 77 by 1, I can divide 77 by 7, and I can divide 77 by 11, and I can divide 77 by 77. These are the factors of 77. The leading coefficient is 1 because the highest term is x cubed. So the number in front of x cubed is just 1, and its factors are plus and minus 1. So when I think about the possibilities, so that means all these numbers will be divided by 1, which means the possible rational zeros can be a positive 1 or negative 1, positive 1, a positive 7 or negative 7, positive 11 or negative 11, positive 77 or negative 77. Now, I am going to test, pick one of these numbers, and I'm gonna plug it in to see if they will give me a remainder of 0, which makes them a 0. So I'm just gonna, for the first one, I'm just gonna try one of the answers. So I want to try negative 1. Let's just try if negative 1 can be a 0. How can I do this? Can negative 1 be an actual 0? I don't know this answer until I perform a synthetic division. So we have 1x cubed, 5x squared, negative 73x, and negative 77. I want to try and see if negative 1 will be an actual 0. Bring down the first number, multiply, add, multiply, add, multiply, add, and I am very lucky. Negative 1 is an actual 0 because we got a remainder of 0. So one of the actual 0 is -1. And the only way I was able to find is once I placed the possible numbers, I just picked one of these numbers and I plugged in to the synthetic division and it worked. Now, why did I pick -1 instead of 1? Again, because of the experience. Quickly, when I was teaching this example to you, I tried to plug in 1 in my head here and I realized that it's not going to give me a 0, remainder of 0. But then I quickly I plugged in -1 into this problem and I knew that I was going to get a 0. So this is what I got. This is how I got the -1. Now, once the synthetic division is over, these numbers, they will create something called depressed polynomial. So now the polynomial we have is less degree than the original problem. So the original problem had x to the third power, which means that it's going to have 3 zeros, right? And then we are only able to find the first one, but we still need to find 2 more zeros for this function. So we're not going to use the original function anymore. We're going to use what we reduce it to. So we reduce it to a 1x squared, because remember, the answer always starts 1 degree lower, and then plus 4x minus 77. This is called a depressed polynomial. And then if I am lucky, this is a quadratic equation. I can factor and solve it. If I cannot factor it, or I don't know how to factor it, I can use the quadratic formula. So now, if I set x squared plus 4x minus 77 to a 0, my factors are x plus 11 and x minus 7. Again, how did I get these two numbers? Positive 11 and negative 7. When I multiply them, their product is negative 77. And when I add them up, their sum is 4. So now take the x plus 11 to a 0, and you will get x equals negative 11. Look, that means negative 11 was among your choices at the very first step. Positive 11 can be a 0 or negative 11 can be a 0. We talked about this. So instead of using -1, you could also just choose negative 11 and do the synthetic division. And then you could just locate the negative 11 as this first 0 at the beginning if you like. And then other factor is x minus 7. I will set this to a 0, and then this gives me x equals 7. This is the other 0. So the actual zeros for this question, the very first step gives me the potential zeros, but the actual zeros are -1. I guessed it and I checked and it was working. And then I got the negative 11 by factoring, and I got the 7 by factoring after I divided my polynomial function by -1. So this question is going to have 3 zeros. This question had one more step. It was saying that once you find your zeros, try to write your function in factored form. If -1 is a 0, x plus 1 will be a factor. If negative 11 is a 0, x plus 11 will be a factor. And then if positive 7 is a 0, x minus 7 will be a factor. And this is how I can express this question in factored form. And this takes care of question 9 for us. The last question on this homework, question 10, is the very same style. So we will need a lot of space. And then we're just going to practice what we did on question 9 one more time. So I'm going to bring this question. We're going to find the real zeros, and then we're going to write the function in terms of its factors. So okay. So the last number is 99, and the leading coefficient is +1. Again, first, I want to find the possible rational zeros. This will be the first step. And how do I find the possibilities? I first look at the last number 99, and I list the factors of 99. I can divide 99 by 1. I can divide 99 by 3. I can divide 99 by 9. I can divide 99 by 11. I can divide 99 by 33. And I can divide 99 by 99. So that's a lot of factors. And the leading coefficient is 1 because we have 1 times x to the fourth, which gives me just a plus and minus 1. Now I'm ready to create the list. All these numbers will be divided by 1, which means we will just get the same numbers on the very first line. These are the all possible rational zeros we can have for this question. These are the only possibilities, and now nothing else will work. Okay, now I want to pick x equals 1 this time and check if it is going to work or not. So I'm going to perform a synthetic division to check if 1 works or not. So we have 1x to the fourth, 10x cubed, negative 20x squared, negative 90x, and last number is 99. And I want to check if 1 is going to work. Bring down the 1, multiply, add, multiply, add, multiply, add, and multiply, and add. So that's very good. Remainder is 0. So we know that 1 is a real 0, actual 0. It definitely works. Very nice. Okay. I want to, again, because this is still a third degree polynomial for me, right? And I can't use quadratic functions yet. This is still a third degree polynomial. I want to pick one other number from my list and see now if I can divide this depressed polynomial by that number I picked and I still get the same remainder of 0. So this time the numbers we're going to divide will be 1, 11, negative 9, and negative 99. And again, I want to just check. I want to test one more time because it might have a multiplicity of 2. So let's try if 1 works again. Bring down the 1, multiply, add, multiply, add, and multiply and add. It didn't work. So that's a very good example that 1, I was thinking about the option that 1 might have a multiplicity of 2, but let's try negative 1 this time. Bring down the first number, multiply, add, multiply, add, multiply, add. It doesn't work. So this is a very good example that how I pick a number, and if it doesn't work, what do? I just change it again. So both negative 1 and positive 1 didn't work. It's okay. This is a good brain gymnastic. So I just have to pick some other number. I go back to my list. My list was 1 and negative 1. I also had a chance of 3, negative 3, 9, negative 9, positive 11, negative 11, positive 33, negative 33. So I think I want to just try the 3 next. So let's just try what happens when I use a 3. Bring down the first one, multiply, add, multiply, add, and I do notice that it won't work. So let's change it to a negative 3, 1, multiply. Now we're going to add 11 and negative 3. So that gives me an 8. Multiply, add, multiply, add, and this is very nice. I finally reached to my goal of getting a 0 as the remainder. So negative 3 is the second 0. So one actual 0 was positive 1. Now the other actual 0 is negative 3. Finally, my function is a second degree function. So I have 1x squared plus 8x minus 33 that I can set this to a 0, and I'm going to try to factor it. If factoring doesn't work, I'm going to use quadratic formula. So this one is just 3 times 11, and then I want to make this plus, this one negative. So when I multiply them, it's still negative 33, and when I add them, their sum is positive 8. So that means one factor is x minus 3, the other factor is x plus 11. So this gives me x equals 3. So that means I made a mistake when I was trying positive 3. Positive 3 was supposed to work as well. And then this one is x minus negative 11. So this question was a fourth degree problem. It was a fourth degree function. So it has 4 zeros, therefore. First actual 0 we were able to find by guessing is 1. So actual 0 is 1. The other actual zero, we found it by guessing and checking. And then the third actual zero came from factoring. And then the last actual zero came from factoring. Now, the second part of the question, writing our function as a factored form, I'll have x minus 1, x plus 3, x minus 3, and x plus 11. This is how we write our function in factored form. And this takes care of our last question for section 5.3, which is the real zeros of polynomial functions.